So the question with which we are going to be increasingly concerned over the next few weeks is we look at some sequence, some series, and we want to know, does that series converge? We won't necessarily want to know what that series converges to. We just want to know, does it converge or not? And that's going to be the question we're going to deal with for the next few weeks. So one thing we can do with this series is we can look at it and say, there are two series that I know about. I know about geometric series and I know about p-series. I know quite a lot about those two. Is this one of those? You can kind of look at it and see that it's not. It's got a part of it that's sort of geometric-y, right? If it was just 2 to the n over 3 to the n, then that would be geometric. And if it was just 1 over n, then it would be p-series. But it's got those things sort of mixed. And if the plus sign were in the top, then I could separate those two fractions and separate the sum. But it's not. The sum is in the bottom of the fraction, so I can't separate that fraction in any reasonable way. So what I want to do is sort of look at the terms and see what's going on with it. So if I put n equals 1, I'm going to have 2 over 3 plus 1. So that's 1/2. And then if I put in n equals 2, I'm going to have 4 over 9 plus 2. So that's 4/11. And then if I put in 3, I'm going to get 8 over 27 plus 3. So that's 8 over 30 reduced to 4/15. Often when you're analyzing the terms of a sequence, by the way, it's often helpful not to reduce the fractions, but I did, so there. Put in 4, I get 16 over 81 plus 4, so 16/89, right? All right, and we don't really need to write out the terms of the series. I just do that to illustrate, what we can conclude about this. So one thing we can look at is, how do I know it's not geometric apart from the form is not correct? Well, maybe it is geometric because we've seen things that don't look like geometric sequences and then turn out to be if you analyze them. So if we look at this one, you'd think, what do I have to multiply times 1/2 to get 4/11? Well, 8/11 times 1/2 would be 4/11. So would it be true that if I multiply times 8/11 the next set of terms, am I going to get 4/15? Well, I don't know what, I do know what 4/11 times 8/11 is. It's 32 121st. Okay, it's not 4/15. Okay, so that allows me to conclude, let's put a question mark on that since that turned out to be not true. Right, our conclusion is that this series is not geometric, and it's also not a p-series. All right, I know it's not a p-series because p-series, the numerator has to be 1. And the denominator has to be n to the p, and so I don't have anything like that. So it's not, p-series is not geometric. What else can I observe about it? What about the limit as n approaches infinity, the limit as n approaches infinity of the terms a sub n? All right, so I could do sort of a careful analysis on this, maybe do like L'Hopital's rule, would find that limit analytically. But you can just sort of look at this a little bit intuitively and say, it's pretty clear that these terms are going to 0. So the limit as n approaches infinity of a sub n equals 0. But unfortunately, that doesn't tell us anything. If the limit of the sequence values was not 0, then I would know that the series would not converge. Since the limit of the terms is 0, I know nothing. All right, so the nth term test is useless. Might converge, might not. All right, so I don't get anything from that. But it's worth looking at because if the limit were not 0, then I would already have my question answered. All right, so I'm still nowhere near getting an idea of whether this series converges or not. So what I need to notice about this series is, although it's not geometric, it's sort of more geometric than anything else. So you ignore that plus n term and it's totally geometric. It's closer to a geometric sequence than anything else. So what if I sort of compare it to a geometric series? How would 2 to the n over 3 to the n plus n compare to 2 to the n over 3 to the n? Well, since I'm adding a positive number to the denominator, this expression must be smaller. And then this expression over here is the same as 2/3 to the nth power. So here, and this is going to be true for all n that are natural numbers. For any natural number n, this term is less than this term. And I know that the sum from n equals 1 to infinity of 2/3 to the n converges because that is geometric. So it converges because it's geometric with r equals 2/3. So absolute value of r is less than 1. But what does that tell me about this sequence? Well, what we're really coming to is a theorem, a way of getting more out of the series that we know. We know about geometric and p-series, so how can we sort of leverage that knowledge to know about some series we don't know anything about? So I'm going to show you a picture first. You probably can guess what the punchline is here, but I'll show you a picture anyway. I like to draw. I'm not very good at it, but I like it. All right, so what I'm going to draw is a not to scale representation of the partial sums represented as an infinite Riemann sum. So this is a Riemann sum with delta x equals 1, so the width of them all is 1, and the height of them is going to be the height of each term, which is 1/2, 4/11ths, 4/15ths. Okay, and so what is important about the fact that since this series, the geometric series, converges, oh, I've messed up this picture actually a little bit. Because what I really want to look at here is the known convergent geometric series. So I haven't messed it up too badly. So what I want to do is represent not this series, but this series. All right. So this series goes, well, I'll put in the 1 first. I'm going to get 2/3, and then I'm going to get 4/9, and then I'm going to get 8/27. I had a COVID moment there. And then 16/81. All right. And then that goes on forever, all right? But our new mysterious series is the terms are always less than these terms. So these terms that I've represented in a sort of sloppy way here, they represent a finite area. If I take all infinitely many terms together, they enclose a finite area. That's what it means that this sum converges. Now, this series being smaller than the convergent series, so those numbers are 1/2, all right, and 4/11ths, which is less than 4/9, right, and 4/15ths, which is less than 18/27. We'll take that on faith, all right. So I'm always adding up areas that are smaller than the areas that I had. So that means that the red rectangles also represent a finite area. And that means that the sum from n equals 1 to infinity of 2 to the n over 3 to the n plus n also converges. Now, what we're going to learn now is to say the reason why it converges is by the comparison test, and that's a formulaic justification that we're going to start using. And we're going to use this a lot, and one thing, we'll talk a little bit more in detail about this comparison test next, but one thing that you want to notice is that we would not, the only way we know about the convergence of the red area because it's less than the black area, but if the red areas could be negative, they could be less than the convergent series, but be going, toward negative infinity. So it's important in this analysis that both the original series, which we're going to call B sub n, and the comparison series, which we're going to call A sub n, they have to both be positive. That means all of their terms have to be positive. So as long as we have a series with all positive terms, and we have another series that is a convergent series and also all positive terms, then if I can compare those two, I can learn something about the convergence of the other series. So we will look at more detail in that next.